Hello, folks. It's George Leoniak, and welcome to New Geometry. Today, I'm going to do a relatively short video, I think, about the squaring a circle, the Great Pyramid of Giza. We'll talk some things about pi and the relationships of these angles, perimeter of the square to the circumference of the circle, variety of different topics that are all going to be kind of bundled together. And we'll look at the work of some other geometers that have applied their relationship to geometry to solve this puzzle. So I'm going to go ahead and share my screen, and we'll start working through this short presentation I have on this material. So yeah, I wasn't really planning on doing a video on this. Recently, I just started working on some drawings related to this again, and just started looking at other researchers' current work on it and some historic work as well. And we're going to talk about these five main themes within this presentation here. We're going to talk about squaring the circle, and we're going to look at it particularly from the perimeter of the square being equal to the circumference of the circle in this diagram. There's another way you could do this by looking at the area of the square in relationship to the circle. That's primarily the way that it was thought about in the historical context. Both of them are going to yield the same results in the end, basically, because it's all going to revolve around if this is possible in relationship to pi. So we'll get to that in just a moment, the value of pi. So we're going to use, if this works out, the angle of the, in the diagram here would be close to or exactly the angle of the Great Pyramid. That if this was a kind of side view of the pyramid, these would be the dimensions. And this value here, 51.85397, that would be the value of that angle of the pyramid, precisely that angle, that would give you the correct height here to make a circle from this center point. If the half the edge here is 1, that would give you a circumference that would equal the perimeter of the full length of that base if it were the square. So that pyramid angle is really key to discovering this, and we're going to talk about that base angle and really how difficult it is to construct it geometrically with compass and straight edge. So we're going to talk about the value of pi because, of course, to get the circumference of this circle, we have to have a construction that can create the value for pi that's being utilized in the construction to get this accurate circumference here. And now pi, let's just talk about that for a moment. I have a couple notes here because pi is impossible to construct with compass and straight edge. It's an irrational number, meaning that it cannot be written as a ratio between two integers. Although Archimedes, early representation of this was like 22 divided by 7, which gave you a kind of close approximation to it, but not the precise numbers that we utilize in all our calculations today. Pi is also a transcendental number, which means that it cannot be the solution of any non-constant polynomial equation with rational coefficients. All right. So basically, because it's a transcendental number, this has some consequences, which basically means that it's stating that it can't be constructed with compass and straight edge. And even though a lot of geometers like myself and others continue to try and do this, it's been mathematically proven to be impossible to do so. All right, so that's all about pi. And we'll talk about other geometers' thoughts on maybe there's an alternative value to pi that would be based on the golden ratio. And I'll talk about some of those construction methods to try to decipher if that's true or not. Then we'll also talk about the methods of constructing this and drawing with this compass and straight edge. And pretty much that's pretty much what this whole presentation is about, is looking at various methods to do that. Okay, so what I have on the screen here with this image, and I know we've been hanging out on the slide for a little bit, but it's just setting up the main elements that are all kind of coming together, all coalescing around this particular drawing, this diagram, squaring the circle, related to the pyramid, and how it relates to pi. This is just a diagram that is just constructed on mathematical values in GeoGebra. It's not based on construction that I could do with the compass and straight edge. But this is the kind of truth checker diagram to all the ones we're going to check, because if any of them are 100% true, these values of 51.85397 for the angle of the pyramid would be that. Of course, there's going to be digits to continue on. I just cut it at this particular point. The height of the pyramid here would be 1.27324, and this edge length over here would be 1.61899. Now, look at that. That's very close to the golden ratio, right? 1.618033. This is 1.61899, and this is also close to the square root of the phi, square root of phi, not pi, phi, square root of the golden ratio, 1.2720. That would be the value for the golden ratio, square root of phi. So this diagram, which I said I can't construct it with the technique, that will give you a circumference of 8. And if the base of this pyramid were 2, when we construct a square, kind of like a top-down view, we would have an edge length of 2, 2, 2, and 2. Add up all those edges, we have 8. So the perimeter is 8, and the circumference is 8. Therefore, we have an expression of this version of squaring the circle. Now, these two areas are not equal. The circle area is larger than the square here, but you still would, we could get to that area construction from these values anyway, if we wanted to. Okay, so that's just mathematically generated in GeoGebra. But let's take a look at some of the most accurate representations of this that I've seen. And that some of them come from, I guess Robert Edward Grant's his website has Sir Robert Edward Grant. To respect his new title here, I'll use his Sir Robert. There's a couple diagrams that he's posted. One that is on his blog post there. This one is from May 25, 2022. This 3,000-year-old impossible challenge to draw the Great Pyramid and use it to square the circle perfectly with no measurement. That's this diagram over here. We'll take a look at that in a moment. And then a more recent one, which I think he maybe discovered roughly about maybe 9 months ago or 10 months ago, but there are a lot of videos on it this past summer about how he's come up with a similar result to this one here. That Metatron's cube, the design Metatron's cube, can be used to also create the angle of the pyramid. And he also discusses how that it leads to squaring the circle as well. So let's take a look at the first diagram, and I've zoomed in a little bit more here to take a look at some of the numbers you couldn't see prior. But down here in the corner, it is 51.854. Okay, so that is looking pretty good so far, or that would be rounded up. So 51.8539, so we have 51.854 for that base angle. And if you have that angle, 151.85397 here, in this diagram here, we have 51.854, and GeoGebra rounds up when you set what decimal places you would want to set in. This diagram was done in GeoGebra. At least that's what it looks like to me. So then if we have that, we have an area of 5.093, which would be both the areas of the, looks like he has the triangle, the square, and the circumference would also be the circle here, the big circle, that would also have the same area, 5.093, and the circumference of the circle would be 8 because his base measurement here of his starting setup would be 1, this would be 2 here. So this would be, essentially showing the diagram I showed before. So I just saw this morning. I didn't realize this one was there because I was just going to talk about the Metatron's cube one. So luckily there was a diagram that was drawn that he had that helped me, discover how he created the construction. And I appreciate having all the correct points here and all the details so they could be recreated. And I think it's really important for people who are interested in this subject to learn some of the techniques and skills to be able to check this stuff out for yourself and any of the things that I share on my channel, because it's a really useful skill to have to be able to reconstruct and how to see the patterns and see where the correct intersection lines are and all those things, so we can reproduce each other's work to check it out and see what's going on with the results, because this would be huge. As Robert says, this is a 3,000-year-old problem that geometers have been working on throughout historically, and now it's been, perfect, the circle perfectly with no measurement. So that means that it's precise, it's perfect, it's no imperfection to the construction. And that is if we round the decimals to a particular value. Now, which he had rounded to the fourth, maybe the third decimal point there, but beyond the decimal point. So when we do reveal the true values for all the decimal, all the values beyond the decimal point, all the values, the digits beyond the decimal point, it's not 100% perfect, but that's, in my mind, that's okay, because this is one of the closest representations that I've seen or come up with individually for myself. And I really thought it was cool how he was able to discover these intersections based on the star cut diagram, basically. Find this key intersection to get the circle, to draw this line across here, to send the line for the pyramid, to come up with 51.85360. Okay, so that's the angle, right? 51.8536. And if we test that out to our, the truth tester of the non-constructible one here is 51.85397, right? So it's just a little bit off, but that really means that it's not been solved, right? At least according to the GeoGebra program, which we hope is giving us accurate values and measurements, that if we drew this, we'd both come up with the same result here in the end. But if we round it to particular values, all I have to do is go to here, and then all of a sudden I round up and I have 8. So the circumference would be 8, and the area would be 5.09296 compared to 9282, and the angle would be the 51.85397, which I already went through, down at the bottom. So it's a really cool construction. It got, really, really close, and I like it. I like it a lot. I think it's really neat that we got really close on that one. But it really comes down to that all this stuff is in relationship to that for pi, which is trying to create this diagram squaring the circle is impossible, because it's mathematically impossible to create something related to, I guess, this whole diagram is related to a transcendental number, which is pi. So let's take a look at the Metatron's cube discovery that has a number of videos posted about it this summer. where Robert, again, which I appreciate him walking through the construction so I can look at how it was done, to go ahead and recreate the diagram in a little bit more of a simplified way without all the circles. But these are the three stacked circles of Metatron's cube, and here are the layout of the familiar kind of star pattern, and where the intersection points are, where we're going to get this large circle here down at the bottom, which is going to give us the base of the pyramid to the center point of the diagram. And, once again, when we do our rounding, some of the digits here, which I have basically taken from this diagram here, and just basically this diagram on the left here is basically I took this and just slid it over to a diagram that had a 2-inch base because I didn't have that in this one. So I just took a parallel line, moved it over here. So this diagram, the Metatron's cube one, produces this 51.85367 pyramid angle at the bottom. And when we place that into our kind of squaring the circle diagram with the 2-inch base for the pyramid using that angle, you'll see that we get a circumference of the circle now in relationship to that square, which has a 8-inch perimeter. For the square, the circumference would be 7.99991. So that is darn accurate. I mean, that is super close when you come up with, of course, taking into account all different types of tolerances, but ultimately it's still not 8. And that's the precision that really needs to be aimed for in trying to do this. Fortunately, from what the hardcore mathematicians tell us, is that the geometers are really on an endless search here. But maybe that's the fun and enjoyment of why we do this in the first place, is to work with the infinite possibilities that are presented, an opportunity for new discoveries that may be just at the tip of right at our fingertips. But ultimately, this is super close, but we can't put this like in the analogs in the historic reference book saying that we've solved this, like many other things, like for instance, I worked on constructing a 17-sided polygon today, which has a constructible method that is 100% accurate. And I came up with one that was not so accurate by just a little bit, but it was easier to draw. So I really like that, but I'll have to let people know that it's not the 100% method, right? Because we have a 100% method that is a perfect hendecagon pattern. But the one I came up with is not like that. It's the same thing with, the polygons for 7 and 9, 11 and 13, these non-constructible methods. We have methods that are very close, but still not 100% accurate by just a very small error. But the thing is with our human error of drawing, really, by constructing these, we're going to maybe draw it 100% accurate, even if we didn't mean to, even if the construction isn't, because we're close, possibly. I mean, doing hand drawing, you always have to let go of the notion of perfection. But we don't, this is a very accurate method, that most accurate that I've seen, but it's still, like I said, is just shy of perfection. Okay, let's talk a little bit in this and we'll talk about some other construction methods that I've come up with recently to try and attempt to do the square in the circle. But the golden ratio connection to squaring the circle in pi is a really interesting one because of the edge length of that pyramid here being so close to the value of phi, the golden ratio, 1.61899, but we have 1.618033 for the edge length. And of course, the heights are very close to the square root of phi, 1.27202 here. But the angles are way different, right? 51.82729 and 51 point, of course, 853. So, we have 0.82 and 0.85. Very big difference for this diagram on that angle, even though these measurements are still similar. But when I draw these two diagrams and have them right over top of one another, and also notice that the circumference would be 7.99234 by just what GeoGebra tells me compared to the circumference of 8, of course, on this diagram. But I could draw this easily. Like, this is an easily constructed design because we can construct the golden proportion in a number of different ways, and it's easy to just construct this this version of squaring the circle, which isn't actually squaring the circle, but it looks like it. It's very close to being it. And if you zoom way in here, right? And this is the yellow golden line over here is the perfected one, and over here is the golden ratio one, which is not 100% accurate to the circumference of 8. This is the difference between the two circles, is 0.001. So that's the difference between A1 and Z there, of how much of a small error it is, which you're not going to be able to tell with your pencil lead at all. So, it's almost a little silly. And with the advent of being able to test all this stuff out, which we're really living in a kind of amazing time to do this, to be able to really look at all the ancient constructions or the older constructions that we've had for a while, or even the ones we haven't had for a while, like Metatron's cube, and really test out all the ratios, look at angles with super high precision. And that allows us to do super accurate constructions that we might have never come across otherwise. So it's really an amazing time to get involved with sacred geometry if you're an explorer like I am, to go ahead and utilize both your hand-drawn techniques in conjunction with this technology to really come up with some of the most precise methods that can be done hand-drawn as well. So you can kind of reverse engineer a lot of things. And that's what new geometry has done a lot of. KNEW geometry. Okay, so let's take a look at this lovely construction here, which doesn't rely on the angle of the pyramid, just a nice design to come up with this version of squaring in circle, which, of course, as we know, doesn't square the circle unless the value of pi is not the way we think it is, which is the value of pi being the 3.141. There's some people out there who believe that the true value of pi is related to the value of phi. And that value would be the square root of phi, 4, the number 4, divided by the square root of phi, would give you this number, 3.144. And it has more digits, which I'll show you later. But that's the main difference. It's either 3.141, that's the standard value, or this value, 3.144. Now, I mentioned Archimedes' value a little while ago, because Archimedes used a technique which was called a method of exclusion. Basically, he took a circle and he made a hexagon in it, which is easy to do, and he made more and more hexagons. And then he took the difference between an outer polygon and an inner polygon and kind of squished it down until he found this edge of the circle in between all of those, or the distance between them, and kind of came up with the calculation of what was pi for like 1,000 years, which was 3.142. And then some Chinese mathematicians did it with like a 12,000 sided polygon and came up with even more precise value. But that was still hovering around 3.141, not really close to 3.144. And if you read about the history of pi on the Wikipedia page, for instance, there's a cool history there that talks about how much historically has, what the value, how it's been constructed, and like how modern supercomputers, however they're doing it now, are getting trillions of numbers, digits after the decimal point, trillions of digits after, or however many digits. But they're all coming up with 3.141 as at least the start. We're coming close to it. And of course, Archimedes' value was 3.142, which, so 3.144 is really pretty different than all the other expressions that have been presented of the value of pi. But it has some nice, it really fits because we could draw it easily, or at least a construction here. This would all be a squared circle. If the value for pi was really 3.144, then we would be able to square this circle, and we all this diagram that I showed you right here would be squaring the circle. This circumference right here would be 8 if this was, but GeoGebra will never tell me that this is 8 if that's is, because it's based on the other value of pi. So I'm going to talk about some little experiments I did that are really impossible to solve, and I love to see a better proof because it would be pretty cool to see if this were the value. But from what we understand, it's a transcendental number that cannot be constructed in any way by any non-constant polynomial equation or the ratio between two integers. So, us geometers are really at a loss for figuring this out, but phi is one of our best kind of easy way to do this. So let me just talk about this diagram because I came up with this in the summer and never shared it in another video. I guess I was waiting for some more information to kind of make a more full, well-rounded video like this. So here's one of my tests. And if the value of pi were 3.144, this would all work out perfectly, right? So notice the circumference here says it's pi, right? Which is the circle, this black circle, the big one, the dark one. So that would be the circumference of that, because the diameter of that circle is 1. So this is pi, the circumference. So the big black circle, B3 to C3 there is 1. Okay, so that's circumference of circumference of pi, 3.141. Now, in that same construction, if I extend the edge of that pyramid in the squaring circle diagram down to the base of a long line that I did, what I basically come up with is another edge length. It's the same length of the edge of the square. I thought that was cool. So this square edge length is basically being reproduced 1, 2, 3, 4 times. 1, 2, 3, 4 times. So just basically picture this circle here as if it's just unraveled itself from this point, and we've just stretched it all the way out. And if I add up all those numbers of 1, 2, 3, 4, this 0.78615 number, well, I get 3.14461. Well, that's the value for Jane's value of pi. He calls it Jane pi. The true value of pi, as he also calls it. It's been called by others. It's not just him. There's a few other people that also feel this. And I actually lean that way quite a while. And this is more up in the air kind of discussion because I'd really love to get to the bottom of this. Because I love the mathematical beauty of it. All this stuff works out. If this is the edge of the square, it's 3.14461. And if that has the relationship to the circle, well, that would mean that the circumference and the perimeter would be the same, and that our value for the circle would be 3.14461. And that would be a kind of way to show that the value of the circle circumference based on this pyramid, based on the one that's based on the phi measurements, would all work out as giving us a perimeter of square equal to the circumference. So let's take a little closer look at that whole thing. So basically, I just took that circle. Here's the length, 3.14461. This is just removed everything from the diagram above, just to focus on this. So if this were 1, and this length, unraveling the circle, just going whoop, all the way over to Z2 from W2, this value, this length would be this length, of course, because it's, like taking a string, holding it in a circle and opening it up, where the length wouldn't change. So this would be 3.461. But this says pi, right? And this is GeoGebra. And pi is not, in GeoGebra, pi is not 3.14461, right? It's 3.141 and whatever the rest of the digits are, 3.141. But so we have a big difference of two digits there, 3 digits. So what I did here was I basically told GeoGebra, I said, let's make our, determine what the circumference, I constructed something that had a circumference of 3.14600605511, and I made it the same length as this, right? So I unraveled that, and I said, okay, my circumference is this, and when I stretch it out in a long line, unraveling the circle, it's this, they're the same. But here's my issue. I checked the diameter, oh, it's 1.00959. Of course, that's to be expected because GeoGebra will never show me that this all of a sudden is 1, because this circumference is not pi. So basically, one of the best tools we have that I have to be able to test this out using some mathematics, besides just hand drawing it and saying so, will never get out of that loop, basically, because the value of pi is programmed into GeoGebra as 3.141, and there's no way for me to actually test out if the circumference would ever be anything other than that. With the diameter is 1, so any value that I plug in as a new circumference value is always going to be a relationship to that. So the diameter here is going to be 1.009 if I've changed the circumference to 3.144. So how do we really test this out? And that's where I've never seen a great proof of this that really shows how this could be true. Because this value in all the historical references isn't even represented, from supercomputers all the way to Archimedes and before him. We haven't seen this number 3.144 show up. They're all about 3.141 or 3.142 from all these greatest mathematician minds throughout history. So, is pi really just the 3.141 and this is it? And we have to be living with our transcendence, unconstructible, non-constructible methods that we'll be stuck with for this one. But we can at least plug in these numbers and create this diagram. But what is really the height of the Great Pyramid? Was it based on phi? Was it based on this type of Metatron's cube diagram, or this type of diagram, or any of these other ones, or between just a ratio of like 11:7? A variety of different ratios could be used, or 22:7. What are the ratios? And so really it's still up for debate of what the actual technique, in my mind, and if the pyramid height is actually dead on precisely that value. But I guess if the pyramid was made to encode any super difficult information for us ever to discover, would be, and if it was 100% accurate, would be the circumference of the circle, which would be, giving us the true value of pi. That would be amazing, because you could see it's so difficult for us to come up with a geometric construction of that for it to be built at such a magnitude, at such a huge scale, with all the huge blocks that went into that, to come up with a value that is actually 51.85397, which in degrees, minutes, seconds, which you also see, would be 51 degrees, 51 minutes, and 14 seconds. That's the thing. That's what it would be for the degrees minutes. So you'll see that interchangeably used. And that's what some people have referenced the pyramid angle to actually be. Now, whether they're reverse engineering that and basically saying, well, it must be pi, we'll use that. Or some people have said it's based on the Great Pyramid angle, based on the golden ratio, like these diagrams I've showed you, and we use Kepler's triangle, which this is also called Kepler's triangle. Whoops, let me get to Kepler's triangle. Half of this is called Kepler's triangle, the 1 square root of phi edge. That's Kepler's triangle. Some people think that's the Great Pyramid angle. So there's a lot of confusion really about that, and I'm not here to say that I have the answer to that. But because there's so many varying angles on the web about what the precise angle actually is. So more research to be done there. And if we could really get precise number, I don't know who to trust anymore on that. Okay, so as a side note, anyway, this little diagram, because we also have this Russian pyramid, which Charlie Zeiss has really made popular here in the States at least, and worldwide for more people to know about. But the Russians built these pyramids, a lot of them, 20 or something of them, 76.345. And I have a lot of information of this on my website if you're new to the channel to check out. And when I first came up with this construction for the pyramid, which gives you that precise angle down at the bottom, the measurement at the base, because this is how this is constructed, is easy. Just from here all the way down to the bottom of the square intersecting the circle, the base is the value for pi. Not the value for pi, the Jane pi value, 3.14460. So that's the value at the base if we start with the 2-inch radius circle for this design here. And I was like, dude, that's super cool. And then I, went on and constructed all these other diagrams I was showing you because I was like, man, maybe I have the key to figuring out this squaring the circle thing. But the golden ratio, is so different. The values are so different than what GeoGebra is going to give me. I'm not able, like I said, to test it accurately. But hey, I'm just going to keep trying. Not all the time because there's a lot of other things to explore. But every once in a while, it's fun to get into this. And I appreciate the work of Sir Robert Edward Grant, going ahead and sharing his discoveries on it. I'm thankful that at least he shows the constructions so I could go back and look at them and really see if they're solved. Because if they are solved, then that's a great technique to use. If they're not, we should keep looking. So when we do say that something is 100% perfect, that almost kind of closes off or seals that exploration a little bit for some people. So it's good to keep it open-ended. And if it isn't solved, so that someone out there just loses their inspiration for coming up with trying to crack that unsolvable puzzle. So I'm glad to have went back and looked at what he's done and showed that there's still more to be discovered there if we can ever get to it. And these are just some recent discoveries or methods or techniques that I was playing around with here, as I was hoping to have a big unveiling at the end here and say, wait, look, we did the impossible, but we didn't. But we got some pretty cool constructions that I like a lot that are still pretty neat based on the square view method or the twofold axis here that, have a simple technique similar to Robert Edward Grant's in the way that I used that big circle and kind of got the idea from him to try that out and how to construct that in this orientation rather than using the threefold symmetry. But I didn't come up with as a precise estimate here because in this, if the circumference of the circle here is actually 8, then my edges of the square in here would be 2.00009. So pretty darn close again, but still not 100%, unfortunately. I used the parallel line method and brought that over to a diagram over here so I could show you the circumference, and that is 7.99963, which is also very close, but still not 100% with this technique. And I came up with this other near miss here as well. It's not as good as the previous ones, but so far, Robert Grant's methods seem to be the closest that we've come to it. But this is a cool construction, and I look at the ease of the construction too, of how easy I could set it up, because sometimes the ease of the construction will be more accurate than a more difficult construction that's more precise, if that makes sense to you, because fewer steps lead to less error accumulating. And if you have tons of steps to do doing hand drawn, by the time you get to your end angle or whatever your result of you're looking for, you'll actually have more error in it than if you have few steps that may be more accurate in the end. But when we use the computer like this to do these are kind of the real truth checker. Here I came up with a 51.85901 base angle, which then will give me the circumference. And I just slid that up to here so we could test it against that. So a parallel line up to the top. So I check it against that circumference, 8.00145. So that would be the circumference of that. It's still not 8 if the perimeter of this would be of the square. I don't have the square there, but it's on these clover points. So that would be 8, the perimeter of the square. So it's still not 8 for the circumference, but a nice simple technique. So I kept going and I was like, let me try some different type of circle templates. So I tried a 5-fold method as well. And once again, it's kind of a portion of a 5-fold method. It's based on the golden ratio. And there's a ton of this angle actually in this that I never knew. It's 51.85 858737. So that's also pretty close, 51.85. That's supposed to be a 4 there, but it's well, what is it again? Let me see what the precise angle is at the top here. 51.85397. So this one is off as well, but from a totally different type of circle template. Whoops. We have 51.8587. But so when I test it against to give me the circumference here, and this is from this construction, I just used a parallel line to test it against my square, which has a 2-inch edge length, hence the perimeter of 8. Then all of a sudden I come up with circumference 8.001. So that's also really close, that I never knew was in the 5-fold symmetry patterns, but it's there as well. And it's really there a lot. So that was a neat little side discovery. And there's also this construction, which is the iconic New Jerusalem design by John Michel, which is based on the star cut diagram. Another way to draw this New Jerusalem setup, which has a 3-4-5 edge length at the top of these triangles on either side. This was probably one of the most, one of the first design that got me introduced to squaring the circle, or coming up with squaring the circle, and thought it was squaring the circle for a while. But still, it does not, it gets very close, 7.99678 for the circumference, and the angle is 51.842, which should, for the perfected one, 51.843. So also a very close method. Now remember, in the hand drawn, you're going to draw this and it's going to be as close probably to any of the techniques I've shown you that are hand drawn are going to be as close to squaring the circle you can do. In fact, you draw them, you probably can't tell much of a difference between them, one from the other at all to the eye. That's why I say with the advent of this digital way of for the amateur geometers out there to really test this, the ones that aren't in the ivory towers doing all this mathematics, the ones that are just using the sacred geometry to explore these mysteries, this is, and if you're hand drawing this, you never really know the difference. So it really then comes down to, well, what's the technique? What are the methods you like to use? What is easy to do, giving you nice results that you enjoy? And have fun with them, because they're all awesome and they all show different relationships between the 5-fold, 3-fold, different circle templates. So there's a lot more to explore there. So this, let's see, my last slides here is, Lego has made a pyramid now for this year that I happen to see. And I wanted to know if Lego has the answer. Shouldn't be a little T at the end of has. Does Lego have the answer? And so I put the whole perfected square and a circle diagram on there to check it out. And it's off by quite a bit, but the Lego bricks have not succeeded in constructing a perfect angle of the pyramid that would give us a relationship to pi, but it still looks like a super cool set and for a Lego set. But the circumference on this one would be 7.511, and I don't have the actual diagram to test it out. It might be slightly better than that or worse. I don't know. I took a best guess on this, so I don't want any Lego representative to get upset that I shortchanged their angle, but it's pretty far off, so I don't think it matters. It's not as close as any of the other ones. So that's my overview on squaring the circle, relationship to pi, some golden ratio connections, some drawing, a lot of drawing methods and constructions. A lot more to be discussed, and hopefully, I'm sure there will be, for those who watched this all the way through, there will be some opinions about what I've shared here, and that maybe there is a true value of pi is the golden ratio one. I'd love to find out more about that and have some great conversations with other interested geometers about this iconic diagram, which is related to this superstructure, great wonder of the world, of the pyramid, that may be encoding this angle to this precise precision that should actually give us the circumference of, which would give us a relationship to pi and actually square the circle with 100% accurate. If that is true, that is a monumental accomplishment to do it at this gigantic scale, like I said before, and we can't even do it on paper or Legos. So thank you for watching the video. I will be back with some other cool videos soon, and check out the new geometry course site. I do have a whole video section on a whole course on drawing the golden ratio Russian pyramid and the Giza pyramid, with a lot of golden ratio constructions in that one that you can check out, and building forms and things like that. And check out some of the other courses. I'm not teaching any apprenticeships right now because I'm teaching the Archimedean solids masterclass for the next 2 apprenticeship cycles. So I'll be doing that again in March. But the Archimedean solids class is going fantastic, and that will be made available in the future, which would definitely take you far in your journey of exploring sacred geometry when that's available. All right, so thanks for joining me. Check out the new geometry courses. Subscribe to the channel if you appreciated the video, and I'll be back again with more. Much love and appreciation. I'll talk to you later. Bye-bye.